All right, in our last video, we took a look at graphing systems of inequalities. When we graphed a system of inequalities, we needed to make sure we were using dotted lines and solid lines appropriately, depending on the sign. We also needed to shade. Often we ended up with a double shaded region, and then we talked about yesterday how everything in the double shaded region would be a possible solution to the system of equations. Today we're going to talk about linear programming. Linear programming is the process of finding maximum or minimum values of a function for a situation defined by constraints. So I'm not going to write the words in, I need you to write the words in. Again, linear programming is the process of finding maximum or minimum values of a function for a situation defined by constraints. The inequalities are called the constraints. Constraints is C-O-N-S-T-R-A-I-N-T-S. The intersection of the graphs is called the feasible region. Feasible region. The maximum or minimum value of a related function always occurs at one of the vertices of the feasible region. If you need to rewind the video and get any of those vocabulary terms, go ahead and do that now. The steps to use linear programming are to, first of all, graph and shade all of the constraints. Remember, the constraints are your inequalities. Then label all of the vertices of the feasible region, and then substitute each of the vertices into some equation. Now, the equation will be the situation that you're trying to maximize or minimize. And then once you've substituted each of the vertices in, you'll be able to clearly identify what value is the largest and at what ordered pair that happens. Maybe you're looking for a minimum though. So let's put this to work. In this situation, we have three constraints. Our constraints are x is greater than or equal to 0, y is greater than or equal to 0, and x plus y is less than or equal to 8. So I'm going to graph each of these constraints. The first constraint is that x is greater than or equal to 0. Remember that x lines are vertical, so I'm going to draw a solid line like so through the x-axis at 0. And then I can draw that over the whole span of the graph. I'm not going to shade yet. I'm just going to draw a little arrow to remind myself which way to shade. Again, I'm looking for this feasible region, which would be the intersection of all of my shadings. Next up, I'm going to graph y is greater than or equal to 0. So y lines are horizontal. Here is my horizontal line through y equals 0. And then I have to shade greater than or equal to. So greater than or equal to will be above that solid line. And then the last constraint is x plus y is less than or equal to 8. Now I'm going to use the intercept method to graph. So for my x-intercept, x plus y, I'm going to think of it as just an equality. X is equal to 8. So on the x-axis, here's 1, 2, 3, 4, 5, 6, 7, 8 right here. And then for my y-intercept, again, x plus y, I'm thinking of this as an equality. I'm going to zero out the x. Y is equal to 8. On the y-axis, 1, 2, 3, 4, 5, 6, 7, 8, right about there. Connect the dots with a solid line because my symbol is underlined. And then it says y is less than, so I need to shade underneath that line. And through my arrow pointing, it's really easy for me to identify that multi-shaded region, which we call the feasible region. I'm going to go ahead and color that in, kind of shade it in. So anything that lays in this multi-shaded region would solve this system of three equations. It would solve the system. Again, my system would be x is greater than or equal to 0, y is greater than or equal to 0, x plus y is less than or equal to 8. So any point in here, any point would satisfy all three of those three inequalities. But I am looking for a maximum or minimum. This is a linear programming problem, so what I'm trying to do is maximize some objective function. So my objective function is c is equal to x plus 2y. So maybe c stands for the cost, and what we're doing is manufacturing like two different things, maybe baseballs and footballs. So if we have this objective function, then we can maximize or minimize it by looking at the vertices. So the next step is to identify your vertices, and I have 3 vertices. The vertices are just the corners of the region, nice sharp corners of the region. So I have 3, 0, 0, over 8, up 0, and then this last vertex is over 0, up 8. Over 0, up 8. Now I plug those into my objective function, which is c equals x plus 2y. This table is handy because I see exactly what I need to plug in, 0 and 0, and I'm going to get out a 0. And then I plug in 8 and 0, and I get out 8. And then I plug in 0 and 8, and I get out 16. So with linear programming, your maximum and minimum values will always happen at the vertices. So to answer the question, how can I maximize the situation? Well, my maximum value will be 16, and it occurs at the point 0, 8. So if X were baseballs and Y's were footballs, I would want to sell 8 footballs to maximize my cost or something. I don't know. I'm just making that up right now. Now, if I wanted to minimize, I would end up with a minimum value of 0, and that happens at 0, 0. So selling 0 baseballs and 0 footballs, for example. All right, so that's a brief overview of linear programming. In class, we will look at some actual examples and do some programming on situations where we'll want to intentionally find probably a maximum value, which would be like maximum profit, or maybe a minimum value, which would be like maybe cost of production. All right, good work. See you tomorrow.